By the early 1990s, opening a personal computer could reveal more about its intended world than the badge on the front panel. In a typical home or office machine, a broad ribbon cable often disappeared into a hard drive, using the interface most buyers knew simply as IDE. By then, the arrangement had become routine. A replacement disk could be bought from a computer shop, mounted in a drive bay, connected to the system, and configured with only a modest amount of technical knowledge. Walk into a graphics studio, engineering department, or server room from the same period, and the storage hardware might tell a different story. Several disks could share a SCSI bus with a tape unit or optical device, managed through a host adapter, and arranged according to rules that demanded more attention. The distinction was not merely cosmetic. It reflected two paths that had formed years earlier, when the industry was still deciding how much intelligence should live inside a storage device and how much should remain elsewhere in the computer. To see why that question mattered, it is necessary to return to an era when installing a hard disk could feel less like adding a component and more like assembling a small machine within the machine. Early hard drives, used by personal computers, were not the self-contained products later generations came to expect. The spinning platters, actuator heads, and supporting electronics formed only part of the complete storage system. A separate controller board inside the computer handled crucial tasks and translated the host's requests into signals the drive mechanism could understand. Interfaces such as ST506 and ST412 became familiar in early hard disk installations, linking the mechanism to its controller through multiple cables. The relationship demanded care. A drive had to match the expectations of the adapter. Geometry settings could matter. Low-level formatting might be required before the operating system could use the disk. None of this seemed extraordinary to technicians working at the time, because computers still exposed much of their internal complexity to the people who owned and maintained them. That arrangement had practical reasons. Electronics were expensive, disk technology was changing quickly, and placing substantial control logic on a reusable adapter allowed one part of the system to handle work that later would migrate onto the drive itself. Yet the disadvantages became harder to ignore as the IBM-compatible market expanded. An additional controller consumed an expansion slot and raised the bill of materials. More cabling complicated assembly and service. Compatibility could depend on details that ordinary buyers neither understood nor wanted to learn. The hard disk had grown too important to remain a specialist upgrade. Business software grew larger, operating environments demanded more space, and manufacturers increasingly wanted to ship machines with fixed storage already installed. What had once been acceptable in a relatively small technical market now stood in the way of scale. A different response to the problem had begun taking shape before IDE entered the vocabulary of PC users. At Shugart Associates in the late 1970s, engineers developed the Shugart Associates System Interface, or SASI, under the leadership of Larry Boucher. The project approached peripheral communication from a broader angle. Rather than forcing the host computer to control every device through details closely tied to a particular mechanism, SASI created a command-oriented relationship. The computer could request an operation, while the peripheral handled more of the work required to carry it out. The shift sounds modest when described in a sentence, but it changed the level at which a system could think about storage. A disk no longer needed to appear merely as a mechanism waiting for finely detailed instructions. It could behave as an intelligent target that understood a defined set of commands. The idea attracted attention beyond one company. As manufacturers and standards groups refined the concept, SASI evolved into the Small Computer System Interface, better known as SCSI. Its ambition reached beyond hard disks. The architecture was intended to provide a common way for computers to communicate with different classes of intelligent peripherals, which made it useful for equipment that did not fit neatly into the consumer PC model. Tape drives could participate. Optical devices found a place. Scanners and other specialized hardware could use the same broader command framework. A workstation designer was no longer limited to thinking about one disk connected to one controller. The storage subsystem could take shape as a collection of devices with distinct roles, all coordinated through a common interface. That flexibility suited professional machines especially well. A publishing workstation dealing with large page layouts might need fast disks for active projects and tape for backup. An engineering system could depend on removable media or specialized peripherals, unavailable to ordinary desktop users. Servers faced another kind of pressure. Storage requests did not necessarily arrive one at a time from a single person. Several users could be reading and writing data while background tasks continued, making device behavior under sustained activity more important than the experience of launching one program from a home computer. SCSI's command-oriented design gave hardware makers room to address such demands without reducing every peripheral to the same simple role. The move from SASI to SCSI also changed the scale of the discussion. What had begun as a manufacturer-driven interface was turning into a foundation other companies could build around without depending on one supplier's private design. By 1982, the name SCSI had been adopted, and the work of standardization gave equipment makers a clearer target for interoperability. That mattered because professional computing rarely stayed inside the boundaries of a single vendor's product line. Disk and tape hardware from different manufacturers might have to work through a third-party host adapter, making precise, shared rules essential in real installations. The standard, therefore, carried an economic promise as well as a technical one. Manufacturers could compete inside a common ecosystem instead of forcing every customer into a proprietary chain of peripherals. The architecture also introduced responsibilities that would later shape its reputation. Devices sharing a traditional parallel SCSI bus needed distinct identifiers. Electrical termination had to be correct at the ends of the chain. Cable length and layout could affect reliability. A host adapter added cost and another layer of configuration. These requirements were not arbitrary obstacles added to make the technology difficult. They followed from the fact that the interface was trying to coordinate multiple intelligent participants on one bus. In professional environments, that trade could make sense. A workstation that cost several $1,000s was judged by what it allowed its owner to accomplish, not by whether the storage hardware saved a few minutes during installation. By the middle of the 1980s, SCSI had moved from an industry idea toward a formal standard, and its place in higher-end computing was taking shape. Yet the same period brought a very different pressure from the rapidly growing PC business. Manufacturers, preparing systems for a much larger audience, were not primarily searching for a universal peripheral architecture. They wanted to reduce parts, simplify assembly, lower support costs, and make hard disks easier to integrate into machines built in enormous numbers. Those goals would lead Western digital engineer Bill Frank to a specification in 1985 that moved host adapter electronics onto the drive board for the IBM PC AT environment. The change would soon be known through integrated drive electronics, and it would redirect the economics of desktop storage. Before that design could dominate the PC market, though, the industry would have to discover whether simplifying the path to a hard disk could matter more than building the most flexible peripheral system available. That discovery would come quickly because the PC industry was entering a period in which volume could turn a practical engineering decision into a market standard. Once more of the controller logic moved onto the drive, computer makers no longer had to treat every hard disk as a complicated pairing of mechanism and specialized adapter. The host connection could be simplified around the PC AT bus, leaving the drive to manage details that earlier systems had exposed to the controller card. For manufacturers, the appeal was immediate. A storage device that arrived with more of its own intelligence reduced the number of combinations that had to be tested, stocked, and supported. It also encouraged drive companies to compete on a common foundation rather than requiring customers to choose from tightly coupled controller and disk packages. What began as an effort to streamline attachment therefore gained momentum from the economics of compatibility. As more vendors built products around the emerging IDE approach, buyers encountered fewer reasons to remain with older arrangements. The interface spread quickly through IBM-compatible machines, and by the end of the decade, its success had created a new problem. Different implementations did not always behave identically. That pressure led to the AT attachment standardization effort in 1989. ATA gave the industry a more formal specification for an architecture that had already become commercially important, turning a popular design into a clearer target for drive makers, motherboard companies, BIOS developers, and system integrators. The distinction between the names could be confusing even then. IDE remained the familiar commercial label, while ATA increasingly described the standardized interface behind the products. Users rarely cared about the vocabulary as long as the drive worked. What mattered was that fixed storage was becoming easier to treat as a replaceable part of the computer. A new disk could be purchased for greater capacity without replacing the entire storage subsystem, and manufacturers could design machines around an interface expected to remain available across many product generations. The commercial effect reached beyond the disk manufacturers themselves. As motherboard design evolved, functionality that once demanded a dedicated storage card could be absorbed into the standard PC platform, removing another purchasing decision from the buyer. That change altered expectations. A hard drive interface no longer needed to be advertised as an exotic capability, because customers increasingly assumed the computer would already know how to accept one. Retail upgrade culture grew around the same assumption. Capacity became the headline figure, not the identity of the controller that made the disk usable. In practical terms, the interface was succeeding by becoming less visible. The fewer decisions a user had to make about how storage attached to the machine, the easier it became for drive makers to compete on size, price, and performance instead. This did not make installation effortless. Early IDE systems could still require BIOS geometry settings and connecting two devices to one channel introduced jumper choices that would later become famous as master and slave. Yet the difficulty had shifted. The owner was configuring devices within a standardized environment rather than solving the older problem of matching a low-level drive mechanism to a separate controller design. That reduction in uncertainty mattered more than the remaining inconvenience, especially as software packages expanded and graphical environments placed heavier demands on disk capacity. Fixed storage was moving from premium option to expected equipment, enlarging the market for compatible drives, just as manufacturers were learning how to produce them in greater volume. Competition improved capacity and pushed prices down, allowing hardware once associated with costly business systems to move steadily into ordinary desktops. SCSI traveled through the same decade under different market pressures. Its formal standard gave workstation and peripheral manufacturers a common architecture that could accommodate far more varied configurations than the typical desktop required. Unix workstations, publishing systems, technical machines, and servers often benefited from the ability to connect several intelligent devices without treating every peripheral as a separate engineering problem. In these environments, the extra expense of a host adapter did not necessarily look wasteful. Storage might be responsible for valuable project files, database activity, shared user directories, or backup routines that ran long after employees had left the building. The interface was being judged by what the whole machine needed to accomplish, not simply by the purchase price of one disk. As professional systems became more demanding, SCSI manufacturers refined controllers, devices, and software support around workloads that could keep several operations in motion. The bus also remained useful because it was not confined to fixed disks. Tape backup mattered in organizations where losing data could cost far more than buying additional hardware, and removable or optical media could join the same peripheral environment without forcing the system designer to begin again with a separate architecture. That breadth strengthened SCSI's position in markets where expandability had practical value, even as the rules required to manage a shared bus preserved its reputation for complexity among PC owners. Someone installing an ordinary IDE disk might think mainly about the cable, jumper setting, and BIOS entry. A technician working with SCSI had to consider where a device sat in the chain, whether its identifier conflicted with another unit, and whether termination was correct. The contrast became part of computer culture, reinforced by magazine articles and upgrade guides that increasingly treated IDE as the expected desktop choice and SCSI as a path chosen by users willing to spend more for features associated with professional systems. Those reputations were useful shorthand, but they could also distort reality. SCSI was not automatically faster in every circumstance, just as IDE was not inherently slow. Performance depended on the mechanical drive, host hardware, software, and the pattern of work being performed. A fast disk connected through an inexpensive interface could outperform a slower mechanism attached to a more sophisticated bus. What SCSI offered was a framework that could handle certain complex situations gracefully, particularly when several devices or outstanding operations were involved. IDE's strength developed somewhere else: scale. Its growing installed base gave chipset makers, BIOS vendors, computer manufacturers, and drive companies strong incentives to improve the same ecosystem. Capacity rose without forcing buyers into a new architecture each time they upgraded, while faster transfer modes and increasingly common motherboard support made separate add-in hardware less necessary. The effect accumulated quietly. By the early 1990s, a mainstream PC designer could count on IDE drives being available from several suppliers. Service departments already knew how to install them, and replacement units could be sourced without rebuilding the machine around a new controller. Software companies benefited indirectly because larger disks no longer required their customers to adopt unusual hardware before installing more demanding applications. The interface was becoming part of the supply chain, rather than a feature buyers had to evaluate on its own. SCSI maintained influence for almost the opposite reason. In machines where storage performance or peripheral flexibility directly affected the work being done, the extra cost represented a small fraction of the system's value. A graphics workstation processing large files, a server answering requests from many clients, or a computer coordinating disks with backup devices could justify hardware that looked extravagant beside a family PC. This division never formed a perfect border. Enthusiasts sometimes installed SCSI equipment in high-end desktops, and cost-sensitive professional systems could use IDE. The important development was that both paths had matured enough to compete beyond their original niches. As the decade advanced, faster ATA modes would challenge assumptions about consumer hardware. SCSI would continue raising the ceiling for demanding systems, and arguments over which interface was truly superior would move away from architecture alone. Real workloads, not labels, were about to become the harder test. The harder test arrived in the everyday work performed by real machines, where reputation often proved less useful than context. By the middle of the 1990s, magazine reviews and enthusiast discussions increasingly compared IDE and SCSI as though the interface name alone could predict the speed of a computer. In practice, the result depended on far more. The mechanical disk itself remained the dominant limit in many situations. Rotational speed, seek time, cache behavior, firmware, controller quality, and the pattern of requests could all matter as much as the nominal capabilities of the connection. A premium SCSI drive attached to a capable host adapter might excel under sustained professional use. Yet a newer IDE model could feel just as responsive in a desktop whose main tasks involved launching applications, opening documents, and loading games. The difference became clearer when the workload changed. A single-user PC often asked the disk to do one thing, finish it, and move on. A server could receive several requests in quick succession, forcing the storage subsystem to decide how to organize work efficiently. SCSI had evolved with this kind of environment in mind. Its command structure and support for multiple devices gave manufacturers room to optimize behavior under heavier activity, especially when a machine had to keep several operations moving instead of waiting for one request to complete before considering the next. This did not make every SCSI system faster, by definition. It meant that certain workloads could take better advantage of what the architecture offered. The distinction mattered because the personal computer market was expanding in a direction that rewarded adequacy at enormous scale. A home buyer did not purchase a storage interface in isolation. The decision was buried inside the total price of the machine. If an IDE disk delivered enough capacity and acceptable responsiveness, spending more for a SCSI host adapter and a higher-priced drive could be difficult to justify. Manufacturers faced the same calculation, multiplied across thousands of units. A few dollars saved on each system could become a major advantage in a market where competing brands fought aggressively over retail price. As volumes rose, the economic cycle reinforced itself. More PCs shipped with IDE support already present. Drive companies responded with additional models. Component suppliers refined chipsets and firmware around the same expectation. Service technicians saw the hardware more often and became quicker at diagnosing it. Retailers could stock a wide range of capacities without worrying that every customer needed a specialized controller. None of these changes looked revolutionary on their own, but together they made the interface increasingly difficult to displace. The mass market was not asking which architecture offered the greatest theoretical flexibility. It was rewarding the one that fit smoothly into a standardized production system and created fewer reasons for the buyer to hesitate. Capacity growth accelerated that advantage. Software distributions were getting larger, multimedia titles demanded more room, and graphical operating environments encouraged users to keep more programs and data on local disks. Each increase in storage demand created another opportunity for an upgrade. IDE manufacturers could address that demand with products aimed directly at ordinary PCs, often without requiring buyers to purchase a new host adapter. For many users, the installation still involved opening the case, checking jumper positions, and entering BIOS settings, but those steps were becoming familiar rather than exceptional. Familiarity has enormous economic value. Once a procedure is understood by computer shops, hobbyists, corporate support teams, and manufacturers, the cost of changing to something else includes more than hardware. Training, documentation, inventory, and service practices all become part of the installed base. SCSI continued to thrive, where those considerations were outweighed by different priorities. In a workstation used for computer-aided design, digital publishing, scientific analysis, or media production, storage could influence how quickly expensive work was completed. A server faced an even harsher calculation. If several employees depended on one machine, slow disk behavior or limited expansion could affect an entire organization. In that setting, the extra expense of a capable SCSI subsystem might disappear beside the value of the work passing through it. Professional drive makers also pursued performance characteristics that were less important to the average household. Faster spinning mechanisms, robust duty cycles, advanced command handling, and host adapters designed for sustained activity all helped preserve SCSI's reputation in demanding environments. The interface's broader device model added another advantage. Organizations often needed backup and removal media as part of the same operational plan. Tape drives were not glamorous, but they were essential in businesses where data loss could be catastrophic. Keeping those devices within a familiar architecture simplified certain professional configurations, even if the initial setup required more expertise. By this stage, the market had stopped behaving like a simple contest in which one standard waited to eliminate the other. IDE had become deeply embedded in the economics of the desktop, while SCSI remained valuable, wherever storage performance, peripheral variety, or continuous operation justified a more elaborate solution. The overlap between them was where the most interesting arguments appeared. Enthusiasts building expensive home PCs sometimes adopted SCSI because they wanted the fastest drives available or liked the flexibility of a multi-device chain. Small businesses could choose IDE to reduce costs on systems that did not need enterprise-oriented hardware. Video editors, musicians, and graphics professionals occupied a shifting middle ground, constantly reassessing whether consumer storage had become fast enough for tasks that only a few years earlier seemed to require SCSI. That pressure forced the ATA world to improve. Faster programmed I/O modes appeared, followed by greater use of direct memory access, allowing data transfers to rely less heavily on constant processor involvement. Later, Ultra ATA revisions raised interface bandwidth again. These developments did not erase the differences in command architecture, but they changed the practical question for buyers. A professional user who once needed SCSI simply to obtain acceptable throughput could now compare newer IDE drives and ask whether the remaining benefits justified the price. Each generation made that calculation less predictable. SCSI advanced as well, with faster variants, wider data paths in some implementations, and continued refinement of command behavior. High-performance disks remained an important part of the ecosystem, particularly in servers and workstations, whose workloads could expose weaknesses that were invisible on a home desktop. Yet the existence of faster SCSI standards did not stop the consumer side from moving upward. Instead, the two markets began to press against each other. Consumer hardware borrowed performance once associated with professional systems, while professional storage moved towards still higher reliability, concurrency, and scale. The old labels survived, but their meanings became more fluid. By the late 1990s, a high-end IDE drive could outperform older SCSI equipment in ordinary desktop tasks, while a well-designed SCSI subsystem still held advantages under workloads built around multiple outstanding requests and several active devices. The argument over which was better became increasingly meaningless unless someone first asked better for what. That question reshaped the way buyers evaluated storage. A gamer cared about level loading times and price. A database administrator cared about sustained response under many requests. A video editor wanted reliable throughput for large files. A corporate server needed dependable operation and a path to expansion. The same disk benchmark could not represent all of those priorities. Once the industry began thinking in terms of workload rather than prestige, the reasons behind the long coexistence of IDE and SCSI became easier to understand. Each architecture had found conditions under which its compromises made sense, and improvements on both sides kept moving those boundaries. The next turning point would come not from another round of faster parallel interfaces, but from a physical problem hidden inside the cables themselves. As signaling rates climbed, moving many bits side by side across wide ribbon connections became harder to manage cleanly, and the storage industry began preparing for a future in which the familiar parallel designs of both camps would eventually give way to something narrower, faster, and fundamentally different. That narrower future began to take shape as engineers confronted a problem that had little to do with marketing and everything to do with physics. Parallel interfaces moved several bits at once across neighboring conductors, an approach that worked well enough while signaling rates remained modest. As frequencies increased, keeping those signals synchronized became harder. One line could arrive slightly earlier than another. Electrical noise and crosstalk became more difficult to control. Cable design mattered more, and the generous ribbon connectors that had once seemed practical began to look like obstacles to further scaling. The problem was not unique to storage. Across computing, engineers were discovering that a smaller number of very fast serial connections could outperform wide parallel buses, while simplifying routing and improving signal integrity. The storage industry was heading toward the same conclusion. Before that transition arrived, users still had to live with the habits of the parallel era. On an IDE channel, adding a second device often meant inspecting a tiny jumper block on the rear of the drive and selecting a role labeled master, slave, or cable select. Those names later sounded more dramatic than the electronics behind them. The settings simply helped determine how two devices sharing one channel would be distinguished. A misplaced jumper could prevent a disk from appearing at startup or cause confusing behavior that sent an owner back to the printed diagram on the drive label. SCSI demanded a different kind of attention. Each device needed a unique identifier, and the physical ends of the bus had to be terminated correctly. Once a system grew to include several internal and external peripherals, troubleshooting could become a careful process of checking IDs, connectors, cable order, and termination. These tasks belonged to an era when the person installing hardware was expected to participate directly in the machine's configuration. Modern users are often insulated from such details because firmware and operating systems perform much of the negotiation automatically. In the 1990s, hardware still revealed its rules to the person holding the screwdriver. That culture shaped how upgrades were sold and understood. Manuals mattered. Diagrams mattered. Computer shops earned money not only by selling components, but by knowing how to make them coexist. A technically confident user could save money and tailor a system precisely, while someone less experienced might pay for installation simply to avoid the risk of an expensive mistake. The next generation of storage interfaces would not eliminate complexity inside the computer. but it would move much of that complexity away from the user. By the end of the decade, ATA had been pushed through several faster modes, and the familiar 40-conductor ribbon cable had evolved into an 80-conductor version that added extra ground wires to improve signal integrity while preserving the same basic connector. This was a clever extension of an established design, but it also demonstrated how much engineering effort was being spent to keep parallel signaling viable. SCSI underwent its own series of refinements, including faster transfer modes and variations designed to increase bandwidth, yet higher speeds made bus length, termination, and electrical behavior increasingly demanding. The industry could continue refining both architectures, but the physical transport beneath them was approaching diminishing returns. Serial ATA emerged from this pressure with a promise that went beyond raw speed. The new interface replaced the broad ribbon cable with a much narrower connection and gave each device a dedicated point-to-point link rather than asking two drives to share one channel in the old arrangement. This changed the installation experience immediately. There was no need to decide which disk would be master and which would be slave. The cable was smaller, easier to route, and far less disruptive to airflow inside increasingly powerful PCs. The first generation of SATA did not instantly make every drive dramatically faster, because mechanical disks still spent most of their time waiting for heads and platters rather than saturating the interface. Its deeper advantage was architectural headroom. Serial signaling gave the standard a cleaner path toward future speed increases, without repeatedly widening cables or tightening the timing margins of parallel transmission. Manufacturers could preserve much of the familiar ATA software model while replacing the electrical connection underneath it. That continuity helped adoption. Operating systems, applications, and users did not need to relearn the meaning of a hard disk simply because the cable had changed. PC makers gained a tidier internal layout. Motherboard designers could integrate the new controllers directly into chipsets, and consumers gradually came to see SATA ports as ordinary features, rather than premium additions. The older parallel form did not disappear overnight. For several years, motherboards carried both interfaces because millions of existing drives and optical devices still depended on PATA. Transition periods in computing are rarely clean. New standards succeed partly by respecting the investments already sitting in homes, offices, factories, and repair shops. As replacement cycles move forward, the wide ribbon cables receded from new systems, and the term IDE slowly became associated with an earlier generation. The professional storage world made a comparable physical transition without abandoning the command traditions that had given SCSI its identity. Serial-attached SCSI, or SAS, replaced the shared parallel bus with high-speed serial links designed for servers and enterprise storage. The move changed cabling and signaling, but it did not discard the richer command architecture that professional systems had relied upon for years. This continuity is one reason it is misleading to say that SCSI simply lost to IDE and vanished. Parallel SCSI faded, yet the broader SCSI family survived by moving on to newer transports. SAS became a natural home for enterprise disks and storage arrays that still needed capabilities associated with sustained workloads, large device counts, and professional management. Its design also reflected lessons learned from decades of bus configuration. Point-to-point serial connections reduced some of the electrical complications that had made traditional SCSI chains difficult to scale at higher speeds. Storage systems could grow through expanders and controllers rather than by stretching a single shared parallel cable farther than its signaling could comfortably tolerate. For system administrators, the visible hardware changed. For software and storage logic, much of the command heritage remained recognizable. The same historical pattern appeared on the consumer side. SATA looked physically unlike PATA, but it preserved enough of the ATA lineage to make the migration practical. The industry was not replacing every layer at once. It was changing the part that had become the bottleneck while protecting what still worked above it. By the middle of the 2000s, this serial shift had largely redrawn the storage landscape. Desktop PCs and laptops increasingly relied on SATA hard drives. Servers and enterprise systems moved toward SAS or other professional storage technologies. Optical drives followed the consumer transition. The wide ribbon cables that had defined the visual identity of PC interiors for decades began disappearing from new machines. Yet the most important consequence of the serial era was still ahead. Hard disks remained mechanical devices, and no matter how efficient the interface became, their heads still had to move across spinning platters to find data. For years, that delay had hidden many limitations of the connection between drive and computer. Once storage stopped depending on moving parts, the balance would change. Solid-state memory would expose the interface itself as a new obstacle, forcing designers to ask a question that neither IDE nor parallel SCSI had been built to answer. What should storage look like when the medium can respond far faster than a mechanical disk ever could? The answer began with a change in the storage medium itself. Solid-state drives removed the moving heads and spinning platters that had shaped disk performance for decades, replacing mechanical delay with flash memory capable of responding far more quickly. At first, many SSDs entered personal computers through SATA because that interface was already everywhere. The choice made commercial sense. Motherboards supported it, operating systems understood it, and users could install a solid-state drive without rebuilding the rest of the machine. The early experience was transformative. Applications opened faster, boot times shrank, file access felt immediate compared with mechanical disks. Yet the success of SATA SSDs exposed a new limitation. The interface that had been designed to serve hard drives was now attached to media that could deliver data far more quickly than rotating storage ever could. The bottleneck had moved. For years, engineers had concentrated on improving the drive itself because the mechanics were slow. With flash memory, the connection between storage and the processor became increasingly important. PCI Express offered a much faster path, and that path created an opportunity to rethink not only the cable, but the command model above it. NVMe, or Non-Volatile Memory Express, was developed for storage attached through PCI Express, with an architecture designed around the low latency and parallel nature of modern solid-state memory. Rather than inheriting every assumption from mechanical disks, it allowed many commands to be processed through multiple queues, reducing overhead and making better use of hardware capable of handling several operations at once. This was not simply another step in the IDE lineage, nor was it a direct replacement for SCSI in every environment. It represented a new stage in which ideas, once associated with different parts of the storage industry, began to converge. Consumer systems still demanded easy installation, broad compatibility, and reasonable cost. Professional machines continued to value queue depth, concurrency, reliability, and scalable management. Modern solid-state storage increasingly had to satisfy both sets of expectations at the same time. That convergence would have been difficult to imagine when early PC owners were selecting controller cards and entering drive geometry by hand. A laptop could now contain a tiny module connected directly through PCI Express, capable of moving data at rates that would have seemed extraordinary in a room-sized storage installation only a few decades earlier. The physical transformation was equally striking. The broad ribbon cable that once defined the inside of a desktop PC gave way first to narrow SATA connections, then in many systems to compact M, two devices that sat directly on the motherboard. The hard drive bay itself became optional. A modern computer could carry enormous amounts of fast storage without a visible cable running to a separate disk enclosure. Yet beneath this apparent simplicity lay a much more sophisticated architecture than the one it replaced. Firmware negotiated capabilities. Controllers managed flash translation and error correction. Operating systems scheduled storage operations through complex software stacks. PCI Express links carried data at speeds that demanded careful signal design. NVMe organized commands in a way intended to keep many operations moving efficiently. The user saw less because the system was doing more. That pattern connected the modern era to the older rivalry in an unexpected way. IDE had succeeded partly by hiding the complexity that early hard disk owners once had to manage directly. SCSI had succeeded where sophisticated command handling and device intelligence justified greater complexity. Modern storage inherited both lessons. The interface should be easy enough that a person can use it without understanding the underlying electronics, yet powerful enough to take advantage of hardware whose internal behavior is vastly more advanced than anything visible from the outside. The division between consumer and professional storage never disappeared completely, but it became less obvious. Enterprise systems still demand features, endurance, redundancy, and management capabilities that differ from ordinary laptops. Servers may use SAS, enterprise NVMe, storage networks, or carefully engineered arrays that exist far beyond the needs of a home user. At the same time, the performance available in mainstream consumer devices has moved into territory once reserved for expensive workstations. A desktop builder can install an NVMe SSD capable of handling many simultaneous operations, with latency far below that of mechanical disks, often without thinking about the history that made such behavior ordinary. That history is easy to miss because successful standards tend to disappear into the background. When an interface works well, people stop noticing it. IDE reached that point during the 1990s. SATA later did the same. NVMe is increasingly treated as a default feature rather than an exotic technology. Each stage follows a familiar pattern. A new design appears to solve a specific limitation, adoption spreads, costs fall, software support improves, and the once new architecture becomes invisible until another bottleneck emerges. The story of IDE and SCSI therefore belongs to a larger history of computing, in which technical progress is shaped as much by integration and market fit as by engineering elegance. IDE was never the most ambitious peripheral architecture of its era, yet its integration strategy aligned almost perfectly with the needs of the mass PC industry. It reduced the number of decisions required to build and service a computer, allowed drive manufacturers to compete within a broad ecosystem, and lowered the cost of adding fixed storage to millions of machines. Its success was not an accident of inferior technology winning through luck. It was the result of solving the right problem for a rapidly expanding market. SCSI followed a different route. Its command-oriented design and support for varied peripherals gave workstation and server manufacturers room to build storage environments that ordinary PC interfaces were not originally intended to handle. The complexity that discouraged some home users could be entirely reasonable in a professional installation where multiple devices, sustained workloads, and specialized peripherals mattered. As the technology evolved, its physical form changed, but the command tradition survived through later systems such as SAS and other storage transports. In that sense, the rivalry never ended with a single victory. The market divided, then the technologies adapted. IDE became ATA, parallel ATA gave way to SATA, and the consumer storage world continued toward increasingly integrated designs. SCSI moved beyond the shared parallel bus into serial and networked forms, while preserving much of the logic that made it useful in demanding systems. Solid-state memory and NVMe eventually shifted the problem again, forcing designers to optimize for media whose speed exposed assumptions inherited from the mechanical era. Looking back, the most revealing difference between IDE and SCSI was not a connector, transfer rate, or marketing label. It was the kind of future each design anticipated. IDE assumed that hard drives would become ordinary enough to belong in almost every personal computer, so the path to mass adoption had to be simple, inexpensive, and standardized. SCSI assumed that computers would need to communicate with increasingly intelligent peripherals, sometimes several at once, and built a framework broad enough to support that complexity. Both predictions proved correct. The personal computer did become a mass-market machine with storage treated as a routine component. Professional systems also grew into increasingly complicated environments, where command sophistication, scalability, and device management mattered. The later convergence of those priorities explains why modern storage feels so effortless from the outside while remaining extraordinarily complex underneath. A user can copy a file without knowing how flash translation tables work, how PCI Express moves packets, or how an NVMe controller schedules queues. That ease is not evidence that the engineering has become simpler. It is evidence that decades of engineering have become better at hiding themselves. The story that began with separate controller cards, wide cables, and carefully configured buses therefore ends not with the disappearance of complexity, but with its relocation. What once demanded the user's attention now happens inside controllers, firmware, operating systems, and high-speed links. The old hardware has faded from view, yet the choices made during the IDE and SCSI era still echo in the priorities of modern design. Storage must be fast enough for the work, affordable enough for the market, reliable enough for the consequences of failure, and simple enough that the person using the computer can focus on the task rather than the machinery beneath it. IDE and SCSI reached those goals by different routes, and their long coexistence showed that there was never one perfect answer for every machine. The most successful architecture was always the one that matched the problem in front of it. That lesson survived the ribbon cable, the SCSI chain, the SATA connector, and the mechanical hard drive itself. It remains visible today every time a computer moves data without asking the user to understand the decades of compromises that made the movement possible.